Mastering the data center MVAC environment requires the precise synchronization of three engineering disciplines: heat removal, fluid chemistry, and deterministic control. Thermal energy generated by server processors acts as a physical entity. This heat must be forcibly extracted from the silicon and pushed through a series of physical mediums, heat exchangers, and industrial barriers before it can be expelled from the facility. This schematic illustrates the trackable heat lifecycle. It traces a single unit of thermal energy chronologically, starting at the IT source on the left, moving through the transport network, and ending at atmospheric heat rejection on the right. Moving that heat successfully requires verifiable data. Every loop and node in this chain demands specific telemetry: flow, temperature, pressure, operating states, and alarms, timestamped and recorded into a central historian. Accepting room temperature alone is a fatal design flaw in a mission-critical facility. Room temperature only indicates if the system is currently surviving. Node-by-node telemetry identifies exactly how the system is operating and how it will respond to a sudden failure. This isometric drawing maps the physical architecture of a hyperscale MVAC ecosystem, separating the facility into distinct operational zones. Inside the data hall, the heat capture zone manages thermal energy using airside equipment, like computer room air handlers and fan wall units, alongside high-density liquid cooling hardware, such as coolant distribution units. Outside the white space, the hydronic transport and exchange zones utilize primary and secondary chilled water pumps, massive water-cooled chillers, and thermal energy storage tanks to circulate and condition the process fluents. On the facility exterior, the outdoor heat rejection equipment transfers the collected thermal load to the atmosphere. Over in the operations suite, the digital nerve center monitors the entire ecosystem through building management and chiller plant optimizing systems. Visualizing this complete architectural inventory is a mandatory prerequisite. You must understand how these macro zones pipe together before you can accurately analyze the physics of any single local control loop. This cross-section shows the dynamics of airside heat capture. Hot exhaust air, indicated by the red arrows, is pulled from the racks and pushed across the cooling coils inside the air handlers. The cooling capacity here is strictly dictated by the delta T, the temperature difference across those coils, and the containment of airflow between the hot and cold aisles. Because we are dealing with chilled water near active servers, dew point margin controls are critical. The automation system constantly monitors humidity and differential pressure to ensure supply air temperatures remain high enough to prevent condensation from forming on the IT equipment. As server densities scale for artificial intelligence workloads, air capture reaches its physical limits. High-density racks utilize coolant distribution units, or CDUs, to capture heat directly at the chip via liquid cold plates. The CDU acts as a strict physical boundary. It utilizes a heat exchanger to completely isolate the primary facility water system from the sensitive technology cooling fluid that physically touches the processors. The performance requirements are substantial. A single CDU can handle nominal heat transfers exceeding 1,300 kilowatts, requiring secondary flow rates of over 320 gallons per minute, driven by redundant variable speed pumps. The efficiency of the entire downstream chiller plant is locked in at this stage. Precise fluid isolation and differential pressure resets at the capture layer dictate the temperature and flow requirements the rest of the facility must support. Once captured, that thermal load moves out of the data hall and into the primary chilled water headers, driven by variable speed drive pumps that dynamically adjust flow based on the real-time processor load. This 3D layout maps the water-cooled chiller plant, which serves as the primary heat exchange engine for the entire facility. Modern hyperscale facilities configure these chillers to operate at elevated temperatures, often supplying chilled water between 27 and 32 degrees Celsius to the liquid cooling loops. Reducing the temperature lift required by the compressors improves the chiller's coefficient of performance, using less electricity to move the same amount of heat. Maintaining that high coefficient of performance requires pristine fluid chemistry. Systems incorporate side stream filtration to remove particulates and automatic tube cleaning systems that fire sponge balls through the chiller barrels to prevent scale buildup. To manage electrical peaks and provide a safety net, facilities install massive thermal energy storage, or TES tanks. These act as thermal buffers, absorbing the data center's heat load during power transitions or while chillers are completing their mechanical restart sequences. Managing a TES tank requires multi-level temperature sensors spanning the height of the tank. This data allows operators to scientifically prove thermal stratification, confirming exactly how much cold water is available at the bottom versus hot water returning to the top. Hydronic transport hinges on the active management of thermal capacitance, chemical purity, and absolute pressure stability. These variables keep the chiller plant operating within its optimal thermodynamic envelope. This rendering illustrates the final physical step, the outdoor cooling towers, where thermal energy is transferred from the facility's condenser water loop into the atmosphere. The engineering choice for heat rejection is entirely dependent on site-specific climate data. The local dry bulb and wet bulb temperatures dictate the physical limits of evaporation, which in turn establishes the maximum possible cooling capacity of the towers. This heat rejection matrix compares the three primary architectures used to release the facility's thermal load. Open-circuit towers offer the highest absolute heat rejection by spraying condenser water directly through the air for maximum evaporative cooling. However, exposing the process fluid directly to the atmosphere introduces biological risks, like Legionella, and heavy water contamination that requires aggressive chemical dosing. Hybrid adiabatic systems isolate the process fluid inside a closed coil. They operate dry to conserve water, only deploying evaporative wetting pads when ambient wet bulb temperatures spike and force the system to seek evaporative assistance. Because evaporative cooling is bound by atmospheric physics, the highest historical wet bulb temperature of the local region establishes the absolute heat rejection floor. That meteorological metric ultimately determines the total safe megawatt capacity for the entire data center. The physical pipes and pumps only function because they are governed by digital control networks that dictate industrial fluid dynamics millisecond by millisecond. This controls architecture diagram maps the rigid, multi-layered hierarchy that separates hardwired equipment safety from software-driven optimization. At the base, Layer 1 contains the physical field devices, the temperature sensors, pressure transducers, and valve actuators touching the fluid. Immediately above is Layer 2, the deterministic control layer. This consists of local programmable logic controllers, or PLCs, executing hardwired safety interlocks and basic run permits for the heavy machinery. Above the PLCs sits Layer 3, the Chiller Plant Optimizing System, or CPOS. This supervisory layer is a software engine that continuously ingests facility data, calculating the most efficient way to stage chillers and trim pump speeds to achieve the best possible kilowatt per turn efficiency across the entire plant. There is an absolute safety mandate in this hierarchy. The supervisory optimization layer must never be allowed to bypass local equipment safety. If the optimization network crashes or external communication is severed, the Layer 2 PLCs are programmed to ignore the silence. They fail safely and independently, instantly reverting to local deterministic sequences to keep the fluid moving and the servers cool. In a fault-tolerant Tier 4 environment, algorithmic efficiency is a secondary goal. It must never supersede the hardwired protection of the mechanical assets. Before a single production server is installed, the facility must survive a rigorous commissioning lifecycle. This timeline maps the governance gates, moving from early design review to final integrated testing, where each successive level scientifically closes the risk of the preceding level. During Level 2 static checks, engineers verify physical installation quality. They conduct strict pressure and leak tests on the piping network and physically calibrate every field sensor against certified instruments. Level 3 moves to startup testing. This stage requires powering up local controls, completing point-to-point verification between the sensors and the PLCs, and mapping cause and effect responses for every local alarm. Level 4 introduces site acceptance and heat load tests. Temporary load banks simulate server heat up to 100%, proving the mechanical plant satisfies thermal loads while adhering to ASHRAE guidelines. Finally, Level 5 executes the Integrated Systems Test. Known informally as pulling the plug, this stage violently tests the boundaries between normal utility power, emergency generator power, and the active cooling redundancies designed to bridge the gap. A facility's reliability is not defined by its design specifications. It is only considered operational after its physical components survive this sequential risk-closing gauntlet. This testing dashboard maps the precise methodology used during Level 5. We systematically inject specific, catastrophic failure modes into the facility while it operates at 100% thermal load.
When we manually trigger a chiller or pump trip, the team watches the automated response. We record the discharge rate of the thermal energy storage tanks and measure the seconds it takes for reserve chillers and standby pumps to spin up and assume the load. For liquid cooling zones, we simulate pipe ruptures. The system must prove its leak detection capability by using pressure decay sensors to identify the drop in pressure and automatically actuate valves to isolate the smallest possible branch, protecting the surrounding IT gear. We also test the digital architecture by forcing sensor failures and deliberately severing the network connection to the building management system. This definitively proves that the Layer 2 PLCs will abandon optimization and execute their local fallback safety sequences. Passing these tests require time-aligned evidence. We use synchronized clocks across the facility to align historian trend logs, verifying exactly when a fault occurred, when the system reacted, and when thermal stabilization was fully restored. MVAC mastery is achieved when time-synchronized data proves your ecosystem autonomously recovers from catastrophic failure, maintaining the trackable heat lifecycle from end to end.